Okay, on this lecture, we're going to look at leaving groups and how the leaving group characteristic affects both SN1 and SN2 mechanisms. The leaving group can be either good or bad. And how do you rate the leaving groups? The best leaving group is one that when it comes off, it is a stable entity. For instance, if you were to compare water versus hydroxide as a leaving group, if after the leaving group leaves you make water, that's more stable than something charged like hydroxide. And so what we would find is water leaves faster than hydroxide does because it's a better leaving group. So charge is very important. Uncharged leaving groups, and when we say uncharged, we mean that after it's already off, is going to be a more stable leaving group than one that's charged. When it is still on the compound, the leaving group is going to have a positive charge if it's going to be negative after it comes off. Excuse me, if it's going to be neutral after it comes off. Something that is neutral when it's on the carbon will be negative when it comes off. Iodide is a better leaving group than bromide. Why? Iodide is bigger and better able to stabilize a negative charge. It's basically, we say there's less charge concentration with iodide because it's a bigger atom. So the bigger the atom, the better it is as a leaving group. Likewise, if the charge is stabilized by something like resonance, it's going to be a more stable leaving group after it leaves, and so then is a better leaving group. The leaving group effect is important to both mechanisms. Both SN1 and SN2 have to have a reasonable leaving group for them to occur. For SN1, because the only thing in that step is the leaving group leaving, the characteristic of the leaving group is particularly important. With SN2, because you have the nucleophile coming in and the leaving group leaving, the characteristic of the leaving group is not quite as important. It's still important, and you can't have a crummy leaving group, but if it's a mediocre leaving group, you can have the reaction go ahead. So let's look at this summary chart, and it gives you various leaving groups. This tosyl is a special leaving group. It has a negative charge on it, but what do you see on this is that you have the negative charge is stabilized by resonance through this. If you look at the structure of tosyl, it's given to you in the book, and this is the way that we abbreviate it. It's a sulfur ion that has several oxygens attached to the sulfur, and that negative charge gets spread across several oxygens. Here, these are good leaving groups. Why? Because the halogens are stable with a negative charge on them. Of course, iodine is better than bromine, which is better than chloride. And then we have water and alcohols as good leaving groups. But the only time we ever see these as leaving groups is if you have an acidic solvent. Why? Because then the oxygen on the carbon will be protonated, and then it leaves as a neutral leaving group. Fluoride and all these other things are horrid leaving groups, and you don't ever see them participating in any kind of nucleophilic displacement. Now, when you have to realize that, for instance, if there's an alcohol functional group, can we get it to leave? Yes, but it's only through protonation that changes the leaving group into water. Now, your book is going to emphasize iodine, the halogens, as leaving groups, and so, iodine is better than bromine, which is better than chlorine, which is better than fluorine. What you find is nucleophilicity increases going down the table, and also so does leaving groupability because of the larger atom effect. So now, knowing what you know about leaving groups, which one of these compounds would react fastest with methanol? Well, All of these are the same, have the same carbon structure. They're all a tertiary carbon, and they're going to react in an SN1 reaction with methanol. With an SN1 reaction, the leaving group is particularly important. Iodine would be the best leaving group, then bromine, then chlorine, and then fluorine. So the fastest one would be the T-butyl iodide. Bromine would be pretty darn fast. Chlorine would be reasonably fast. And fluorine, the fluoride, would be very slow. If I look at these two reactions, which one would be faster? Okay, if I look at the two substrates, I see they're primary, so I know that it's going to undergo an SN2 reaction. If I look at the nucleophile, that is the same. I look at the leaving group and I see this one is an amine and this one is a tosyl. You've seen that tosyl is one of the best leaving groups that we have, and an amine is an absolutely horrid leaving group. The leaving group that we would have forming from this, I'm going to draw it for you, would be this leaving group. It would be nitrogen and 2 hydrogens and a negative charge on it. This is very, very basic, and because it's so basic, it would not want to form. However, the leaving group here is the tosyl group, and so that would be TOS with an oxygen on it and a negative charge on it. And that negative charge is spread out over several oxygens, and so it's stabilized. So the fastest reaction here would be the one with the tosyl leaving group right here. This one is so slow, it doesn't even happen. You could mix it all day long. Okay, which one of these would be faster? Essentially nothing happening because the leaving group is so horrid. If I look at this reaction, you can see that I'm having iodide coming in and displacing the bromine or the chloride, the bromide or the chloride. So the bromide is a leaving group here and the chloride is a leaving group here. Bromide's a better leaving group. This is an SN1 reaction, so it will leave and then the iodide would come in. And so this one would be faster. Which of these would be faster? Well, since this is methyl iodide and methyl bromide, I know it's going to be an SN2 reaction. Iodide's a better leaving group, and so iodide's going to react faster in this SN2 reaction. It's a better leaving group.